Our previous video was talking about vertical asymptotes. Now we're going to be talking about horizontal asymptotes. When we look at horizontal asymptotes, what we're looking at is the limit as x itself is approaching infinity. Alright? So instead of approaching an x value, a finite x value, we're approaching infinity. Essentially, what this is doing is we're looking at the end behavior of the graph. Okay? So when we're looking at the limit as x approaches infinity, or the limit as x approaches negative infinity, all we're looking at is end behavior of our graph, or our function. Our end behavior is shaped by our horizontal asymptotes. All right. So, again, we're looking at the limit as x approaches infinity, and we're also going to look at the limit as x approaches negative infinity. Okay? Both of these will be telling me about a horizontal asymptote in my graph. I could have one, I could have two. I don't know if we could have more than that. If you want to know, we'll look into it. Okay, but here, based off of this graph, as x gets closer and closer to infinity, so as x gets bigger, my graph is going to come down and it's going to mellow out at -2. So it's just going to hit this flat line and continue down that line forever. And then as x approaches negative infinity, as x gets super negative, our graph is coming up and it's approaching that line of 3. All right? So all we're looking at now as x approaches infinity, positive or negative, we're looking at the end behavior of our graph or our function, and that's based off of our horizontal asymptotes. So what we're going to look at is what is called an end behavior model. Okay? End behavior model. So, if you took my Math 3 class, you heard me talk about horizontal asymptotes. We said top heavy, bottom heavy are equal. That's what we're looking at here with the end behavior model. We're going to look at the highest exponent of each, if the numerator and the denominator of a function, to determine if it's top heavy, bottom heavy, or equal. So, for example, for a top heavy, let's say we have some crazy function. We got 7x cubed plus 6x squared minus x plus 2 all over 4x squared plus 2x minus 1. Okay? All we're going to do is we're going to zoom in on our highest powers in the numerator and the denominator. So what I'm looking at here is 7x cubed over 4x squared. That's my end behavior model. So if I were to reduce this, I'm looking at 7x over 4. 7x over 4 is just a line that looks something like this. Up 7 over 4, whatever. So as x approaches infinity, my graph is going to just keep going to infinity. As x approaches negative infinity, it's going to negative infinity. It's going to behave like this line over the long run. All right? If this would have been a 7x to the 4th, so this would have ended up looking like 7x squared to the 4th, my end behavior model would look like a quadratic instead. So then both my end behaviors would be going to positive infinity. Okay? If it's bottom heavy, so bottom heavies, we just kind of reverse these. Let's say we have h of x equals 7x plus 2 over 4x squared minus 1. Okay, again, we zoom in to the highest powers. So I'm looking at 7x over 4x squared, and when I reduce that, it's 7 over 4x. Okay, if I plug infinity in here, I'm going to get a really, really big number. 7 divided by a really, really big number is going to give me 0. Okay? If I take $7 and I distribute it to everyone in Provo, you practically get nothing, but there's money. It's not 0, but it's approaching 0. So that's what's happening here. Even if I plug in negative infinity, this is going to be a negative bottom, but I'm still going to get closer and closer to 0, but from the under the negative x-axis side. All right, so top heavy, we look at the end behavior model. Bottom heavy will always equal 0, always. And if they are equal. So if I have my function and I have 6x cubed plus 4x squared minus 2 over 2x cubed plus 3. Whatever that function is, okay? Whatever it may be. I still just zoom in on the highest powers like we have here. And I've got 6x cubed over 2x cubed. Since these are the same, it's just going to reduce to 6 over 2. So in this case, 3. So my vertical or my horizontal asymptote is at y equals 3. So as x approaches infinity, we're going to be at 3. And as x approaches negative infinity, we're at 3. So when you're looking at functions, you're looking for, does the top grow faster? If so, what's my end behavior model? Does the bottom grow faster? If so, the answer is 0. If they grow at the same rate, if they're equal powers, then you look at the ratio of the leading coefficients. All right, there's going to be a lot of examples to cover through here. Go ahead and take a look. If you got questions, let me know. I'll see you guys in class.